All right, so on to our second set of slides for dispersion. Calculating the standard deviation is the topic this time. And we're really going to get into our first, no, I don't want to say complicated formula, but a formula that's got a few extra things going on. So I'll try to go slow through this. When you're doing your own calculations, you may want to refer back to this video, watch it a couple of times just to kind of get the process. All right, so standard deviation and variance. S is the symbol for standard deviation, and it's defined by the formula you see to the right. I'll just talk about that in different pieces. First, there's a square root over the whole thing. Don't bother with the square root until you've solved everything else inside. The top part is the most complex part. It's the sum of x minus x bar squared. Well, what does that mean? It means for every person's score, we're going to take their score, subtract the mean from it, and then square that. Once we have that for each person, we're then going to add them up. That's where the sum comes in. Then the bottom part is dividing by the sample size n minus 1. That part's relatively straightforward. So once you've got all of those values, you're going to divide them by the sample size minus 1, take the square root. All right, so just going column to column, I want to show you how I would normally set something like this up. I have a column for x minus x bar, and then one for x minus x bar squared. Just for that first score, we had the mean of 75 from our central tendency slides. 57 minus 75 gives us negative 18, 61 minus 75 gives us negative 14, and so on down the line. Interestingly, if you look at the x minus x bar column, if you add that up, you're going to get negative 32, negative 40, plus 8, plus 13, plus 19. That ends up coming to 0, and that's not a coincidence. X minus x bar is always going to add to 0. This is one of the reasons why we need to square the values. Otherwise, the negatives and the positives are going to even out. If you're doing a problem like this and you keep getting 0 in the numerator, it's because you're adding up the x minus x bars first. You have to square them before you add them up. The next column you see, x minus x bar squared, is where I've simply taken each of these values and squared it. So 18 squared is 324. Of course, the zeros squared remain 0, 8 squared is 64, and so on down the line. In the slide, you can see how I've taken each of those values, 324 plus 196 plus 64 plus 0 plus 0 plus 64 plus 169 plus 361. I've added them together. They come to 1178. So I take 1178 divided by the sample size minus 1. There's 8 scores. Minus 1 is 7. And then I end up taking the square root of that, of what that comes out to. And that gives me 12.97. That value 12.97, it doesn't have much meaning on its own, aside from the fact that we know about 68% of our scores are going to be plus or minus 1 standard deviation from the mean. So the mean plus or minus our standard deviation of 12.97 is going to capture a range that will have about 68% of scores in most distributions. 95% will be captured by 2 standard deviations, but don't worry too much about that value itself right now. What we're going to do with it is we're going to use it to compare with a different distribution. So we're going to see how this value tells us some information that the mean didn't. Looking at the scores for the second graduate assistant, I'm not going to calculate these out for you. I can tell you that it comes out to 2.39, and you can try to calculate that yourself, a nice little practice problem. One thing to note here is that that is substantially smaller than the standard deviation for the first graduate assistant, where it was almost 13. And what that's reflecting is the fact that the first GA scores are more spread out than the second GA scores. The second GA scores only range from 71 to 79, so we're going to have a much, much smaller standard deviation in that case. And that'll always be the case. Anytime you have something that's more spread out, it's going to have a larger standard deviation than scores that are than a distribution where scores are closer together. The variance piece, we haven't talked about the variance primarily because it's not all that useful for our purposes, but it is easy enough for us to talk about. It's simply the standard deviation squared. It's not particularly useful because it's in squared units. So the variance for so the variance for the first distribution would be about 169 squared exam points. We don't think in terms of squared exam points, so not anything that has an intuitive meaning for us. All right, one piece I want to talk about from the formula is something that we'll see at a couple of different forms throughout the semester. And it's kind of one of the, kind of a core statistical value or a core statistical concept that kind of weaves its way throughout the class. And that's what's called the sum of squared deviations from the mean, sometimes called SS total. That's referred to by the formula here, which is actually just the numerator of our standard deviation, the sum of x minus x bar squared. It's got a fancy name, sum of squared deviations from the mean. However, that just really describes what we're doing. We're summing the squared. Deviations from mean just means how far each score was from the mean. So that's just a description of what we're doing rather than a fancy name. We will see this formula and variations of it when we discuss other topics, regression and ANOVA, really a core piece with those. So I'd like to kind of highlight the importance of this value right off the bat. All right, there's lots of other formulas you might see for the standard deviation. If you go online, you will undoubtedly be able to find 5 or 6 or 7 different variations. Don't worry about that. These formulas are correct. I try to use the formulas that best show conceptually what we're doing. There's other formulas that were very popular when people had to calculate things by hand all the time. They were shortcut formulas. So you will see a lot of different variations of the formula. One variation that you'll see is some formulas will use different numerator, a different denominator, I should say, the bottom part of the equation. Some use n rather than n minus 1. Technically, that's the difference between getting a standard deviation for a population and a sample. That is a theoretical definition that you'll see in textbooks all the time. Not very useful because we're pretty much always dealing with samples, so we would never be using that theoretical formula. But again, I do want to highlight, you will see lots of other versions of these formulas. Don't get confused. Just stick with the ones that we use here because they are undoubtedly the ones that would be used in practice. All right, just a little bit on how you would do these analyses with R, and this is also covered in the text of the tutorial. But I've created a data file called test data, and the different variables are just the different GA scores. One thing we can see, basic structure like we saw before, name of the data, $, name of the variable. You can see we can ask for the mean of our variable, which I call GA1, the median. Commands are really plain here. They match the names of what we're looking for. You can't get the mode. There's no mode command, but we can use what's called the table command. What this is going to do is it's going to list out all of the different scores and how many people scored that, and you'll see that in the second set of numbers there, the second row. You see every score had a 1 except for a 75, which had a 2, so that would become the mode. And you can see a simple command for getting the standard deviation as well. You can get the variance this way as well. I think the command is VAR. All of this really straightforward in R. Again, keeping in mind that R is a computing language that is written for statistics. So it's going to have a lot of stuff that is really intuitive.